Everybody here should see a little notification that says that that it's recording. I'm looking here and I see that I've got a fair amount of people on the call. I really appreciate everybody's flexibility. I had a very weird hour ago. It was about 9:30 and my internet at my house went out for a few minutes and then it came back on, but then it went back off at about 9:55. And then between then, there were some issues with Blackboard. I'm curious, for those of you in concrete design, did you all experience issues just getting onto Blackboard? Because I was having a hard time doing that even just on my phone using like cellular network. Okay, so that seemed to be an issue across the board. So we're going to meet today through Teams. I'm going to post this lecture via Blackboard or via YouTube. What I'm going to do for concrete design, and I'll send everybody an email, is that for those of you that are in concrete design, we were supposed to have a homework due Friday. I'm going to cancel that homework assignment. I do want everybody to watch the lecture, but I'm not going to make everybody submit that homework assignment. I am going to do that for steel, though, pending that everything works well. So let me get right into it. Before I do want to mention one very little typo I had in my notes. I'm curious through Teams, can you all see my, well, actually, hold on. Let's do this. Let's do something else. Let's put this over here. Actually, let's try something. Let me not use presenter view. Let's do primary monitor from the beginning. Okay. Can you all see the slides and then see the laser pointer as well? Okay, good. All right, I had a little bit of a typo in my slides, or not the slides, but the notebook calcs that I did in lecture 38. I just wanted to point this out. What I have here in the slides is correct. That's supposed to be a plus symbol. But when I was doing the calcs, I wrote a minus, and that the minus was the error. That's supposed to be a plus right there. So I do apologize. The math that I did assumed a plus. So I did the calculations correctly. Just for some reason, I wrote a minus instead of a plus. For those of you that computed it on the homework using a minus, I gave you full credit because I'm not going to take off for a mistake I made in the lecture. So hopefully that makes sense. Let me go ahead and just get right into today's lecture, and then we will get right to it. I want to go back to discretely braced beam design, and I want to make sure that everybody is comfortable with that process. First off, let's go through how you design a discretely braced beam. I'm going to try and look at the camera here. So let's go through how you design a discretely braced beam. The first thing that you do is you go through and you say, okay, I need to compute MU and VU. And so you assume a self-weight and compute that. Next, you compute a moment of inertia based off your deflection limits if you have them. The homework problem for today is not going to have deflection limits, so you can actually skip all this stuff. I'm trying to make it a little easier on you. Next, what you do is you determine a CB value for your design and an LB value for your design. And if possible, use table 3-1 for your CB quantity. Then what you do is you go to this. So you go to table 3-10, and then off the x-axis, you use your LB, and on the y-axis, you use MU divided by CB, and then you find the point where they intersect, and you go up and to the right and find your first section with the solid line. And once you have that section, you say, okay, let's verify that the moment of inertia is greater than our minimum. And if not, we just skip all this and go to table 3-3 and pick a section. Once we have a section, though, we analyze it. We make sure that it has adequate shear capacity, adequate moment capacity, and it meets deflection limits. So that, in a nutshell, is the process behind designing a discretely braced beam. So if I have a beam, I have got some load on it, and it's discretely braced, that's how I pick the beam. That's how I design it. Now, just real quick, I'm not going to make anybody do this. Don't worry, you don't have to go through this part. This issue is not going to be an issue that you have to concern yourself with. But I do want to point this out. So if you have a beam like this one, where it's really weird, you know, you've got like 3 different unbraced segments. They're all different lengths. The loading's weird. So each segment has a unique CB and each segment has a unique M max. How do you go about design? When you analyze the section, like once you have a trial safe, you analyze all of them. So just pick the one that has the worst case efficiency. But when you're in design mode, how do you design? Like, what do you go into table 310 with? And so my advice is to pick the one with the largest MU max over CB or the largest LB. There's a good chance they're the same segment, and if not, just go with the one with the largest MU max over CB. Again, you're going to have to analyze all of them, so it's not really going to matter. It just might mean you need to iterate a little bit more. The whole iteration is going to make a lot more sense after today, and so I kind of want to illustrate that. Speaking of, let's get right into iteration land. Last time I talked about false positives, and I mentioned it, but we really didn't talk about it. So I kind of want to talk about that today, and I want to show you an issue that can happen when you have a CB value that's high, okay? So I want everybody to break out their manuals, and we're going to use the chat in Teams. I want everybody to break out their manuals, and I want to conduct an exercise with you, okay? So I've got here some data, and I just made it up. It's not anything that goes to a particular example. So we're going to say we've got a beam that has a maximum moment of 10 20-foot kips. And again, I'm just making these numbers up. We have a required moment of inertia of 2,800 inches to the fourth. CB is 2, so it's a lot higher than the examples that we've done so far, the design examples. Like the design example that we did in class had a CB of like 1.14, and then your homework had a CB of 1. So those are low CB values. CB of 2, that's pretty high. So, and then we have an LB of 20 feet. So here's what I want everybody to do. I want everybody to break out their manuals, and remember, you go into table 310, and on the x-axis you use LB, so we'll use an LB of 20, and on the y-axis you've got MU over CB. So MU over CB ends up being 1020 over 2, and 1020 divided by 2 is 510. So I want everybody to go in their manual and tell me, what section do you find that meets these requirements? Now, I'm going to give everybody a sec on this. Let me go to the chat here. I'm going to give everybody a sec. But I want you all to take an LB of 20 and MU over CB of 510, find that point in the table, and then intersect. Tell me which section you get to. Like, what's the first solid line shape? While you're doing that, even throughout all this, I brought my manual. A W24 by 84, okay? That's what I got, okay? So that's the first shape you should find if you go in with 20 foot and 510. Okay, now, somebody else in chat, I want you to do me one favor. I want you to go to the ZX charts, the table 3.2, and for a W24 by 84, tell me what's phi MP. Nothing else, just what's phi MP. $840. All right. So for a W24 by 84, phi MP is $840. Okay, that's correct. Now, here's the problem. Anybody notice a problem with what we found? Okay, it might be a little difficult to see, but there's actually a problem with the W24 by 84. It doesn't work. Okay, here's why. Okay, let me show you what's going on. Here's the problem. Okay, let's take these values. Let's take these values and let's dig into them. Okay, first off, the maximum MU was 1020. That's the maximum applied moment. Okay, that's how much the beam has to hold up. Now, we said that phi MP was 840. See, remember what MP is. MP is the absolute maximum possible capacity. The plastic moment is the maximum capacity that a section can withstand. So this section's no good, okay? What happened is this. What's happening is the process led to a false positive. See, what's going on is you've got your CB term. CB increases your phi MN. Remember, CB is always greater than or equal to 1. So it's taking your moment capacity and it's increasing it. But it can't increase the capacity past MP, past the plastic moment. Remember, your curve goes up, but MP sort of is where it cuts off. Like CB will increase it, but it's cut off at MP. So here's you can't account for that in the design phase. Like in the analysis phase, when you analyze that beam, like if we were to say, let's go ahead and analyze the W24/84, we would get that the capacity is 840 and it's no good. So that's what I mean when I say it's a false positive, that you read a section from the chart, but when you actually go back and look at the phi MP, you find it doesn't have enough moment capacity to hold up the original moment. And that's what's the deal with a false positive. So how do you handle that? Okay, so here's how you handle it. First off, everybody should have gone to their manual, and this is what they should have seen. So if you go to the manual, you go to an LB of 20 feet. So right here, this is LB of 20 feet, and then your moment of 510. Like I made the numbers work out so that it would actually line up, so it'd be a little easier for everybody to find it. That's why it was like 10, 20, and 510. So 510 and 20, that's that point, and you all read the W24/84. So everybody watch the screen. So let's say you look up the W24/84 and it's a false positive. What do? You just go to the next solid line section and then try that out. And if that doesn't work, go to the next one, and then go to the next one, and go to the next one, and you keep going until you just find one that works. Now, that doesn't mean you need to do a full-blown analysis of every single section. You can actually whittle it down really quickly, okay? The one thing that you have to be kind of used to when you're doing this is just be prepared to flip back and forth in your manual, because you're going to look at your design charts and then go to the ZX table. Go to your design charts, go to the ZX table. Design charts, ZX table, so on and so forth, until you find a section that's worth analyzing. And I want to show you how that works for this problem. Okay, so if you have a larger CB value, it might be good to set up like a table. Okay, so here I've got a little table set up, and I'm going to show you how this works. So we've got trial sections, we've got MU and the plastic moment, and then our moments of inertia. So let's take it one step at a time. So the first thing that you found was the W24/84, and you found that from table 310. Okay, so you find that from table 310, and then what do? Well, the MU is 1020. That's the maximum moment on the section. And then phi MP was 840. So it's no good. Okay, now when this is all said and done, you're going to look at the moment of inertia. But right now, this problem required a moment of inertia of 2800. But right now, who cares? Because the section's no good, so don't even bother. Don't even bother looking at the moment of inertia. Okay, and so then we go to the next section. Now, I'm curious in chat, if the W24/84 was the first section that you picked, what's the next one? So going back to that table, so here's the table, go to the next one and tell me what is the, what's the next section past the W24/84? The W27/84, exactly right. Okay, so the W27/84 is the next section. Now we have an MU of 1020. What is the 27/84's phi MP? So now you got to flip back to table 3.2 and tell me what's phi MP. So I want chat to tell me that. And I want somebody else to tell me. $9.15, exactly right. And then that means it's still no good because the 9.15 is less than the 10.20. Now, again, if you want, you could write down the moment of inertia, but again, who cares? So the next shape, and just to make sure that we're moving forward, the next shape, if you go past the W27 by 84, it's a W30 by 90. Now, I'll go ahead and tell you this. If you're having a hard time picking which one to go with, instead of going diagonally, instead of going up and to the right, you can always just trace upwards. And whichever the first solid line you hit after your shape, that's the one you go with. The downside of tracing upwards is that you might trace upwards and then go, oh, I got to turn the page and go to the next one. But if you're trying to whittle down a section, I found it's sometimes a little easier. Now, MU is still 1020. If you look up phi and P for a W30 by 90, it comes out to be 1060. Now, here's the deal. Does that mean that this section is good? Not necessarily. We still have to analyze it to make sure that it has enough moment capacity. All this tells us is that its maximum possible capacity is 1060. It's possible we do the analysis and we find that its actual capacity is like 1015 and it's not enough. But at least now we know it's a worthy section to analyze. Like there's no point in wasting your time on the 24 by 84 or the 27 by 84 because you know it's not good enough. But at least the W30 by 90 has a shot. Okay. And now, once you have a section that's worth analyzing, now look at your moment of inertia. You can read that from table 3.2 as well, and you'll see that it's good. One other thing just to keep in mind, if you get to this point and you've got a W30 by 90 and you think it's a worthy section to analyze, but it doesn't have enough of a moment of inertia, then abandon all this design chart junk and just go to table 3-3. Table 3-3 is the IX tables. Remember how we would select a section based off IX? Just do that, because what that means is that your beam is not governed by moment capacity or shear, it's governed by deflection. So ignore all the beam chart stuff because the beam chart stuff is focused on moment capacity. All right. Any questions? I'm going to stop the share for a quick second because I want to pull something up with on YouTube. I'm still confused on how we found 30 by 90 in the table. Okay, if you go to, so what page are you on? So here, instead of doing it, let me do this. Does the W18 by 86 not work for iteration? Well, let's see. What's the phi and P for the W18 by 86? What's the phi and P first? Before we see if like how we found the W30 by 90, what's the phi and P for the W16 by 86? Hold on. That whatever you said, it didn't pop up in chat. Hold on. Or no, it did. I asked you hadn't replied yet. Oh. So Austin, what is phi and P for a W18 by 86? So it's not one of the bolded sections. I'll go ahead and tell you it's under the 24 by 76. Yeah. No worries, no worries. Now let me get to Mr. Sutphin's question. And given my tech setup today, I think the easiest thing to do is to just pick this up and, oh God, this is a mess. All right, let me see if there's a way I can blow this up. Can everybody see the manual, I guess, as best as possible? Let me see if I can find something to point with. All right, so hold on. I think I need to be here. All right. So this is where we were before. okay, right at this point right here, okay? This is awkward. Okay, this point right here. And then and we went here to the 24 by 84, and then we started going diagonally. Now, started going like this way. Well, if you're having a hard time seeing which one to pick, instead of going diagonally, go straight up and down. So here's the point, go straight up. That's a W24 by 84. And then go straight up. And right here near the top of the page is a W27 by 84. Okay. Now, if you keep going straight up, you're going to go past the page. So what does that mean? Turn the page, go back, and then start going up again, and you'll see how you hit the 30 by 90, which is this section here. And again, if it's still hard to see, you can go back and you can kind of see how that's the shape right there. I apologize. I'm sure this is really, really difficult to see with my camera. Tell you what, maybe if that was confusing, let me know. I can try and pull up the digital copy of the manual. If anybody wants me to pull the digital copy of the manual up, I can do that, and we can go that way. We got time. All right. Is everybody good? Okay. Before we get into our example today, I'd like to discuss a very, very brief coverage of shear, because one of the things we have yet to talk about is shear capacity. And shear capacity is not hard for rolled shapes, but there's some behavior I want everybody to understand. So let me share something real quick. All right. All right. Can everybody see this YouTube video, like full screen? Okay. So what I have here, this is a laboratory test that's looking at a steel eye shape, but it's looking at it from the side. So if you look, you can see how it looks like somebody took a Sharpie and they drew these like grid lines on it. The grid lines are drawn on the web, okay? So if you look at the very, very top and the very, very bottom, those are the flanges. So you've got flanges on the top and the bottom, and then what we're looking at is the web, okay? Now, if you take this thing and you start loading it in shear, what it does is this. So if you look, you can see here, does everybody see on the top right, this like red and white thing that looks like a candy cane? Does everybody see that? So that's a hydraulic piston, basically. It's a super, super hyper fancy piston that's applying force to the beam. So this beam is seeing a lot of shear, okay? And so when you load this thing in shear, you can see it's going like like they've time-lapsed it. And you can see what's happening is it's kind of folding along the center. Does everybody see that? So that's a shear failure. It's also kind of funny how that thing's failing, and it kind of looks like it's at a 45-degree angle, kind of like how concrete beams, when they crack at a 45-degree angle, and they cracked at a 45-degree angle because of Moore's circle. Well, the same thing's going on here. What's happening is if you go from the actuator on the top right to the support on the bottom left, that's experiencing compression. So the steel plate is being folded that way. It's buckling that way. Along the other direction, from the top left to the bottom right, it's experiencing tension. So that's what's called a shear buckle. It's buckling in shear. And it buckles at a 45-degree angle because of Moore's circle. So whenever you see shear buckles and they occur at 45 degrees, it's the same reason why. Now let me go back to the notes, because I want to talk a little bit just about the equations, just so that everybody can see this. So this is the slide. First off, I want to just make sure that everybody's clear. This is an incredibly brief coverage of shear. I'm not giving this topic justice at all. I could spend weeks talking about shear. We just don't really have time. But for a rolled W shape, I'm going to be honest, it really doesn't matter, because if you just look at the numbers, and we've been seeing this on all the beam examples we've been doing this semester, that shear never really was a problem. Like you'd have 40 kips in load and 250 kips in capacity. When you're looking at rolled W shapes, they just have phenomenal shear capacity. Now, a plate girder, on the other hand, plate girders where you're picking how deep the web is and the thickness of the web and the sizes of the flanges, shear becomes a whole nother animal, because where you're picking the sizes, shear buckling can very seriously become a phenomenon. And I could spend weeks talking about that, but we just don't have the time. For a W shape that's made out of 50 KSI, they'll never buckle. I just want you to see it for bridges for later. Now, the way that you compute the capacity is you first compute the nominal capacity, which is 0.6. It's in shear. Remember that 0.6 term from von Mises. Remember, every time we see something in shear, there's going to be a 0.6 there. So we have 0.6 times Fy times the area of the web, which is just D times the thickness, times this shear strength coefficient. And that shear strength coefficient is intended to account for buckling. But if you go to the spec, if you go to chapter G and you look at W shapes that have 50 KSI, it's always equal to 1. So it's only equal to something other than 1 when you're dealing with like custom built sections like a plate girder. The only thing that's a little iffy is what your phi value is. Your phi value is usually 1. The only time it's not 1 is if your web slenderness is bigger than 2.24 times the square root of E over Fy. But if you look at every single rolled shape in the manual, all the W shapes, every single one of them, there's only 8 sections that have that violate this limit, and phi is 0.9. So phi is either 1 or it's 0.9, and the only time it's 0.9 is when H over TW is bigger than that limit. And again, only 8 of them do that. So most cases, it's 1. Does anybody have any questions before we get into our example today? Okay. This is going to be a little strange. I'm actually going to do the calcs with you on MathCAD, because my Surface, when it rains, it pours, I'll tell you. And I've been using a Microsoft Surface for screencasting, and my Surface recently, the screen cracked. So I can't even do the pen cast. I have a Surface today. I have it with me, but the problem is the internet, or sorry, attaching this to the Marshall's internet. I was having security issues, and I couldn't figure them out in the 5 minutes before class, because I just got here like 10 minutes before class. So I'm just going to do it on MathCAD. But I actually think for this example, it's not really going to matter, because a lot of this is pretty tabular. Let me show you what I got going on here. So we got a beam that's simply supported, and it has a point load at midspan. Now we have a 65 kip live load at midspan, and the only other load on it is the self weight of the beam. So we don't have to worry about the dead loads or anything like that. Just this. So the dead load shown does not include the beam self weight. We're going to assume 100 pounds per foot, and we're going to also ensure that this beam meets a live load deflection limit of L over 360. Now these slides are uploaded on Blackboard, and if you look at the next couple of slides, I have done a lot of the math for us. I didn't want to have to chug through all this over and over and over again. I think by now we're good with WL squared over 8 and stuff like that. So I went ahead and just did a lot of this for you. So before we begin, step 1, we look at our moments and shears. And so we have a dead load, or a self weight moment of WL squared over 8. We have a live load moment of PL over 4, 1.2 dead plus 1.6 live. We get a factored bending moment of 525. And then we have the shear. Same thing over here on the right, VL or WL over 2, P over 2, and we get a shear of 53.2 kips. And then CB, if you look at the previous slide, CB was 1.67. I just gave that to you, even though you can look that up and see that it's 1.67 whenever you have a point load at midspan. So MU over CB is 314.4 kips. So there's that. There's the MU over CB and all of that. And then lastly, we have our moment of inertia. So this is a point load at midspan. So our deflection formula is PL cubed over 40 ADI. The allowable deflection was L over 360. So I computed that and I got 0.67 inches. PL cubed over 40 ADI, just solve for the I value, just swap I and the deflection, and you get 968.28. Is everybody okay with that? I don't want to just rush through it if there's any questions, but I figured that this was pretty old hat at this point. Everybody good? Okay, so let's start chugging this thing out. I'm going to start out actually doing this on Excel. So everybody bear with me here. I'm going to stop the share. Oh, you go away. Okay, so we have an MU of 525. We have VU of 53.2. Let me share this. All right. VU of 53.2 kips. And then we have CB of 1.67. So MU over CB is that many foot kips. And then LB for this problem, LB, let's see, LB was 10 feet. All right. So first thing I want everybody to do, I want you to tell me the first shape that you find that meets these requirements. I'm going to give everybody a sec on this, but I want you to find the first section that you can that meets these requirements. So we're going off of those two values right there. W21 by 48. Okay, so W21 by 48. Okay, now MU is 525. Now, somebody else other than Austin, I want to know what phi MN is, or phi MP. So again, this is where you're going to have to flip back and forth. So we've got a W21 by 48. Somebody tell me, okay, 398. So is this section good or no good? No good. Exactly right. So that, don't even waste your time looking at that section. So I'm not even going to fill out the other two columns. Okay, so if a W21 by 48 doesn't work, what's the next one? So again, you know, flip back and forth, I know. W18 by 55. That's what I got. Now, again, we have an MU of 525. What are we getting for fee and P? Somebody else. I don't want like 3 people to be the only ones in chat. I want to get everybody else involved too. I'll start calling on people. So what's the fee and P for a W18 by 55? Miss Payton. I'm calling on somebody. Oh, okay, never mind. Mr. Schwartz beat you to it. All right, so you got 420. So, Mr. Schwartz, is this section good or no good? No good. Exactly. All right. Now, we're going to go with Miss Payton. Miss Payton. All right, so the W21 by 48 doesn't work. The 18 by 55 doesn't work. What's the next section? What page are you on? You should be right around page 3-117. Or is anybody else got a section if the W21 by 48, the W18 by 55, W21 by 55? That's right. That's right. If anybody's having any problems finding these, I mean, please ask. Like, that's what we're here for. All right, I'm on page 3-117. Again, you go up 10 on the x-axis. Okay, there you go. Good, good. All right. Well, I'll call on you for the next one then. All right, somebody else. Let's try Mr. Marone. Mr. Marone, tell me what's fee and P for a W21 by 55. Yeah, this is a difficult lecture or difficult concept to do digitally. So I mean, I do want to make sure everybody's getting this one. You have a fee and P for me for W21 by 55? You're going to get that in table 3-2. I believe that's one of the bolded sections, so shouldn't be too difficult to find. It is one of the bolded sections. All right. Does anybody else have it? 473. There we go. All right. So, Miss Roberts, is that good or no good? No good. There you go. All right. That's fine. That's fine, Brent. Don't worry. Don't worry. I'll call you on the next VMP, though, so be ready. Victoria, why don't you tell me, do you have the next shape? $21 by $62. There you go. All right. Now, Mr. Marone, MU is 525. What about VMP? For the 21 by 62. I think that's a bold one as well. 540. Okay. Now, here's the kicker. Is this a good section or not? Well, the way that I would say it is this. I would say it's worth considering. In other words, we don't know if it's good, but we know that VMP is larger, so it's worth doing the math on. Now, before we move on, Mr. Maroon, I'm going to ask you for one more value. For this problem, IX min was something like 968.28. What's IX for this section? 1330. There you go. So on the deflection side, are we good? Not about moments and shears, but on the deflection side, are we good? Yes, we are. Exactly. So really all we need to check is our moments. Like we could check shears, but we're going to see how shear is, again, not a problem. But moments, we're good. I'm going to leave this up here for a quick second to see if anybody needs to copy some stuff down. And then we're going to transition to another program real quick. Everybody good? All right. I'm going to stop the screen share, and I'm going to transition to another program. This is a program called MathCAD. All right. So the reason why I'm using MathCAD is because you can do the calculations visually. We might talk about MathCAD in senior design next year. So first off, let's write down some values. So C sub B, oh, sorry, it would help if I started typing. C sub B for this problem was 1.67. Okay. What did we find? We found that phi MP was 540 foot kips, and we found well, actually that's all we wrote down. Somebody do me a favor. Somebody in chat tell me what LP is for the problem in question for a W 21 by 62. That's the shape we're looking at. Maybe I should put here. Try a W 21 by 62. What's LP? 6.25, and that's 6.25 feet. Then LR. What's LR? 18.1. So LP and LR are this. And then for our problem, LB was 10 feet. So if we're talking about these quantities, what zone are we in? Zone 1, Zone 2, or Zone 3? Exactly right. Okay. And so the only other quantity we need to confirm our capacity is phi BF. What's phi BF? That's the slope of that line. Somebody else, somebody who hasn't chatted. Mr. Rains. How about Mr. Rains? What is phi BF? $17.5. $17.5. Remember, it's 17.5 kips. So exactly right. So okay. So what we can do then is so how do we compute our zone 2 capacity? Well, it's remember we do that, right? We have to compute that. Nice thing about MathCAD is it sort of does it for us. So I'm just going to set equals and change the units to foot kips. So we get 792.206 foot kips. And so phi mn is the minimum of all of this. Sorry, all of this or that, which is BMP. So let me clean this up a bit. So hopefully, does that look clear? Can everybody read that? So what we've got is we've got phi mn is 540 foot kips, and then we had an mu of, if we remember this problem, mu was 525 foot kips. So that's sort of the big observation that we make at the end. So is this beam worth picking? Is it a good section? Like when it's all said and done, is it good or no good? It's good. So what's our answer? Our answer is use a W21 by 62. All right, I want to give everybody a sec to see if they got any questions. This was a very strange way of delivering lecture with the balance of Excel and MathCAD and all this. And so I do really want to thank everybody for their patience with all the technical glitches and hiccups and whatnot. But I'm going to give everybody a sec to see if they have any questions, and then I want to pull up the homework real quick.
Hey, Dr. Mike.
Yes.
In the lecture notes where you done the MU over CB calculation,
yes.
You had 1020 over CB. Is that an error?
Hold on. Give me 1 second.
I believe it was, yeah, 1020.
Right here?
Yeah. Where it's like 1020 foot kips.
Yes.
Wait, is that right? Or the example part, the example.
Hold on. Are you what we just did in class just now, like together?
Yeah, like the very last slide where we start the example.
This.
Yeah, right there. I believe that's supposed to be 525 instead of 1020.
Oh, yeah, you're right. This right here.
Yeah, I think the number
yeah,
314.
it's copy and paste. Yeah, that's 525.
I was just letting you know that way it's fixed there.
I appreciate that. Yeah, that's supposed to be 525. I'll fix that on Blackboard as well. But yeah, that's supposed to be 525. I just copy and paste the formula from over and didn't.
It ain't a problem. Yeah.
No, I appreciate that. Are there any other questions? I mean, this is good stuff, please. All right. Let me stop the share real quick. I want to pull up the homework because I want to show y'all something. This is your last homework assignment in steel design. Basically, I wanted to give you a problem that was very, very similar to what we've done in class. I just want, the whole point of this assignment is really not to make the structural analysis complicated or to make the CB determination or really the overall problem. I just want to make sure that everybody's good on using this, on using the steel manual, using table 310. So there aren't even any deflection limits, so you don't even need to worry about the moment of inertia. All I'm interested in for this assignment is that you're able to compute MU and VU and all that stuff, and that you're able to use table 310 to accurately select a shape, and that you are able to analyze that shape to verify its moment capacity. I have here a note, which I can probably delete because I say the self weight of the beam may be neglected when determining CB. In other words, you're permitted to use table 3.1, but I gave you the CB values there at the bottom, so you don't even need to look up the CB values in table 3.1. You can just use those. So yeah. Are there any questions? I'll give everybody a minute, and then I want to discuss some very quick housekeeping items. All right, well, I'm going to fix those slides to where that 525 number's fixed, and I'm actually going to re-upload this homework assignment to delete that note because, again, I gave you the CB value, so there's no need to update that. In the meantime, I want everybody to just keep an eye out on their emails. We got one final lecture left, and that's our exam reviews in both classes. Just keep an eye out as to whether or not we do that on Teams or on Blackboard. I'd like to keep using Blackboard, but Blackboard was not very friendly today, so we had to go through Teams. Again, I apologize for the very short notice on that, but I really appreciate everybody's flexibility in joining us today. I'm going to post this recording to YouTube as well. I really appreciate. Will it only be open for a 2-hour period, or will it be longer? I'll probably, so we're going to talk about that on Friday. We've got our full-blown exam review. What I'm going to say is this. I'll probably be able to leave it open a little bit longer just to make sure that everybody has time to, like, I don't want to have any technical issues, but what I can't do is leave it open through another exam period because there are other exams on Monday. And so some of you all might have an exam Monday at, I think it's like 2. So I've got to look at the final exam schedule and see when the other exams are so that I'm not horning in on those periods. So will I leave it open for longer? I'm going to try to, but I also want to say that it's going to be just like previous exams. I know I've got a 2-hour slot on the final, but it's going to be designed to be a 50-minute exam just like all my others. So you should have more than enough time for the final. I've never had students on the final complain on time in class, so I don't think it would happen here. But I'll work with you if y'all have network issues. I'm not. I mean, obviously, if I have them, you all could possibly have them too. But I can't go into the other. I can't horn into the other exam windows. Does that make sense? Yeah, if you, so let me say this about, before we close, let me say one thing, and I'll mention this on Friday. Okay. Everybody, I'm fully aware that people might have network connectivity issues, but hopefully everybody has a phone and you can call me during the exam. If you're having an issue during the exam, and I'll say the same thing to concrete design, if you're having an issue with like uploading or something like that, or there's Blackboard's giving you an issue, like don't just sit there, like let me know, okay, and we'll figure something out. But we'll talk about a lot of this stuff on Friday. It's exam review time, so please come prepared for questions, stuff on the exam. We got that's the whole point of Friday's lecture. Everybody good? All right. Well, again, I really appreciate everybody's flexibility. I will see you all on Friday, and we'll talk about nothing but the exam. That's all I got. We'll see you. I'm going to stop the recording and let y'all go.